Hello, my name is Ashley. Welcome to the Stanford Crowd Course on Practical Machine Learning with Python. Today we're going to be talking about multivariate linear regression. Today you will learn about multivariable linear regression. Before we dealt with univariate linear regression, where we just had one input x. Now we will look at how we can have multiple inputs or features and learn higher dimensional patterns. We will look at the new model representation, cost function, and formulation for gradient descent. We will also look at feature scaling and learning rate selection. Let's look at housing prices. Though we could plot housing sizes versus their price and postulate there could be a linear correlation, we know that the price of a house is not solely affected by the size alone. There might be other features that we can use to explain the correlation, such as the number of stores in each state, the kind of flavors available in each state, the average household income, and much more. Let's extend our single variable linear regression model to include these new features. Instead of just y equals w0 plus w1x, we now have a series of x's because of many different features, generalized to n features. Hence, our new hypothesis is y equals w0 plus w1x1, and so forth, adding successively until we reach wnxn, otherwise known as wkxn. Some more notation to introduce. First of all, as mentioned, we have m training examples and now n features. Also, we have a vector of weights instead of just two weights, where the vector is of length n and hence there is one weight per feature. Now, our input is of m by n dimensionality because there are m training examples and each training example has n attributes or features. Hence, we store these inputs into a matrix uppercase X, which is called the design matrix. Now, lowercase x refers to just one feature vector or one single training example in the matrix when used throughout our other functions. Meanwhile, y is still a vector of outputs that we've always seen. A tiny example dataset has been shown on the bottom right. Now, we can actually represent the sum of weights and input features, called a weighted sum, in terms of a simple linear algebra computation. That operation w to the tx, or the weights vector transpose multiplied by the input features. This essentially computes a dot product between the two vectors w and x, as shown in the diagram. Now, with this form, we can't have constant terms w0 because they aren't attached to any feature. Actually, we can think of them as attached to the feature of 1 because any value times 1 is that value. Hence, we can make x0 always equal to 1 and still have constant terms. The cost function will be the same as before using the new notation for our model. In gradient descent for single variable regression, we computed error derivatives with respect to our two weights w0 and w1, then performed gradient descent to achieve optimal weights. In multivariate, we have n weights, so we must compute n derivatives for each weight and then perform gradient descent to obtain the most optimal weight for each feature. Now, when we update the weights via gradient descent, we must do so simultaneously. That is, if we update weight w1 and immediately update it, this will perturb the cost function derivative with respect to w2, which we do not want. Partial derivatives imply that the other variables are constant, which we need. Instead, we want to store the changes independent of each other into temporary variables, and then once all steps are made, we synchronize the update of the temporary storage to the actual weights. Now, let's talk about feature scaling. Suppose we have two features, the number of house types, for example, bungalow, apartment, etc., usually within 10, and the size of the house in square feet. This can go up to thousands. How do you make sure that these two features are treated equally when they are in different ranges? Feature scaling ensures that input features are in the same range, which provides to also make training much easier and in many cases more accurate. If feature 1 is in the range of 0 to 10 and feature 2 is in the range 0 to 10,000, then the hypothesis will be dominated by feature 2 and its weight, and it would take extremely long to reach the minima. Feature 1 loses its say over the hypothesis function, initially at least. For that, we use feature scaling. A way of implementing this is by making sure all features fall within -1 and 1. This formula will give us the rescaled values between -1 and 1. Now, how do we select the learning rate alpha? Alpha is a very small number that usually determines how large of a step to make using the gradient. When we choose a larger alpha, the change is larger and we may accidentally take a step too large and overshoot the minimum point. With a small alpha, we take many iterations to converge. Thus, we can experiment with the value of alpha to find the best situation for us, called hyperparameter tuning, or even use adaptive learning rates, where the learning rates change over time. For example, they decay over time or even grow over time, of which we will not go into too much depth today. And with that, we finished the material for today. Thank you guys so much for watching. I hope you guys enjoyed and you learned something.
And that concludes our video. This course was created as a part of the Stanford Crowd Course Initiative, the world's first massive online open coursework developed entirely by an online community. If you'd like to learn more about us or view more courses, visit crowdcourse.stanford.edu.